Hello. Welcome to another Pulusound stream. I'm not sure, is this the first one I'm doing this year? Let me check that. Yeah, I think it is. Yeah, last one was December 28th. So, Happy New Year. Right. There's been some interesting news in the audio programming, live coding, algorithm community. This was posted today by Telephone or Julian. James McCartney has just open sourced a project he has been working on since 2011, sapf or sapf, which stands for Sound as Pure Form. And in case you don't know, James McCartney is the original developer of SuperCollider. And so James says about the language, it is a mostly functional, stack-based, postfix syntax language with pervasive auto-mapping of functions over lazy lists in a similar way to how APL maps functions over arrays. It is not a replacement for SuperCollider, but it is a delightful toy that has some nice properties. And also kindly note, James has currently no time for support, which is fair. So let's take a look at the GitHub. It's here under lfnoise/sapf or sapf. I think I'll keep saying sapf because that's shorter. So the source is here on GitHub. Currently I think this runs only on Mac OS. But now that it's open source, maybe someone can contribute support for additional platforms. I happen to be running macOS, so that's fine by me. And here in the releases we can see that there's a binary download available. Released 20 hours ago. And actually, I had some downtime at work today, because I was waiting for Windows and Linux installations to complete. So I had a brief moment to play with this, and also during that time I very quickly wrote something that I think is going to be quite useful here, which is an Emacs mode for sapf. So it's just called sapf.el. You can find it on my GitHub, and yeah, there's installation instructions here. Because right now, sapf is only a command line executable, so you start it up and then you can type code into it and then it runs that. But there's no editor or anything like that. Unlike SuperCollider. So, I actually have this installed already to save us a bit of time, and maybe we can just pretty much dive into it, although I'm gonna drink a bit of my tea first. Oh, also I should get my lip balm because I can feel my lips getting dry already. Okay. So, There's not a whole lot of documentation on this. I mean, there is a fair bit of documentation, but it's text files in the GitHub repo. It's maybe not structured in the most easily digestible way, but I'm sure we can get somewhere with just this. So let me open this folder where I have the README. So if we just briefly look at the introduction here, this program is called a tool for exploring sound as pure form, or sound as pure form, or sapf. It is an interpreter for a language for creating and transforming sound. The language is mostly functional, stack-based, and uses postfix notations similar to fourth. It represents audio and control events using lazy, possibly infinite sequences. It intends to do for lazy sequences what APL does for arrays, which is to provide very high-level functions with pervasive automatic mapping, scanning, and reduction operators. This makes for a language where short programs can achieve results out of proportion to their size. Because nearly all of the programmer-accessible data types are immutable, the language can easily run multiple threads without deadlock or corruption. So, some pretty interesting design goals there. Especially this, a language where short programs can achieve results out of proportion to their size is very interesting from the perspective of live coding and, I guess, writing musical code quickly. I have a bit of prior experience with like postfix or stack-based or concatenative languages, however you want to call it. I had to learn a bit of fourth when I've been working with open firmware on the PowerPC Max, because the open firmware is basically a fourth interpreter. It's quite a fun paradigm to write in. The one major problem with postfix, in my opinion, is that the code is basically unreadable. Because, okay, let's dive into an example. So, I've set up this sapf.el so that I can actually show you from my Emacs configuration here. So this bit, basically you just configure the interpreter path, the arguments, highlight function, that's not super relevant here. Then I have it automatically activated for .sapf files. I don't know if that's a file extension that James had in mind. I think all the code bundled with the program is just in txt files, but I think it's good to have a dedicated file extension. And then I set up some key bindings here to start the interpreter, stop the interpreter, and then also run the code at point. So how does this work? Or how do stack-based languages in general work? Let me start up the interpreter. So basically it starts here, there's some prior output here, don't read it or you'll get spoiled. Tells us the version, the sample rate, something about Manta, I don't know what Manta is. Then it tells us how to get help for all built-in functions, which is nice. So kind of like SuperCollider, there is some form of built-in documentation. And type quit to, well, quit. So, this being a stack-based or postfix or concatenative language, the way this works is we have a stack, and by entering words, we push things onto the stack. So one example of a word, or I guess, yeah, a word might be the number 1, so if I just... Okay, it jumped around a bit because of my scrolling settings, but yeah. Okay, what does this output mean? I guess it printed the last thing and then also the entire stack, so there's a command called prstk for print stack. So here we can see the entire stack. We can push some more items onto the stack. Okay, I guess the first line here is telling us what was added to the stack as a result of this line. And then this is telling us what the entire stack is afterwards. So, oops, I ran that twice. Well, it's fine. Now if I print stack, I can see that all of these things are there. Now, how do we do things other than push onto the stack? Well, we can, for example, enter a plus, which is the addition operator, and what that's going to do... Actually, let me show you the help. So, plus is a function, so if you want to get help for it, we have to quote it with this backtick, and then type help. So this is going to tell us how addition works. This bit here is saying that this operates on the two last elements of the stack, which we're calling x and y here. Then it results in one new element being pushed onto the stack. And importantly, it consumes these two input elements from the stack, or words, or whatever. So what does that mean? It means that when I type plus, it will take the last two elements of the stack, which is the 3 and 4 here. It's going to add those together and then push that onto the stack. So as a result of this, we should get everything up to here, but then a 7 instead of the last 3 and 4 here. And indeed, that's what we get. We have other similar operators like multiplication. Now we should get 14 in place of these two elements. And, you know, division. So that's 1 divided by 14, which is 0.07 something. We have subtraction. We probably have power as well. Yeah, I think that's what that is. Then finally 1 to the power of 3 point lots of things to e plus 22 is just 1 because, yeah, 1 as the base. So that gives us a bit of an idea of how we can do basic math. Maybe let's have a look at the README again. Oh, one important thing to note here is that white space is like all the same, so line break isn't really any different from a space. So, okay, I can, for example, clear the stack. Now we have nothing there. I can also say just 1 to plus, and that's the same as, you know, doing 1, then 2, then plus. So white space doesn't matter. We have comments starting with a semicolon. That just ignores everything after the semicolon up to the next line break. And that's basically the one major tool you have for making your code more readable. Commenting extensively. Okay, README. So there's some motivation here. Why? Talks about other languages that inspired sapf. We're not gonna pay too much attention to that. Okay, I guess here's an important nitpick. sapf is inspired by, but is not purely a concatenative language because it has lexical variables. And that's in fact another thing that's gonna help with legibility. Okay, so here it talks about setup. I haven't actually done any of this, so I guess all these variables have sane defaults. If not, then oh well. We have command line arguments, one of which is the sample rate, and then the other is the prelude file, and the prelude is just like a piece of code to run before it puts us in the interpreter here. So you could define your own functions in there and, you know, have them loaded before your session. Just a moment. Yeah. Okay. And then we have a help flag as well. And here's all the environment variables explained. I don't really care right now. Here it tells us how we can get function help. Well, we already went through this. Here's an important thing to know. Type stop to stop sound playback. And here's where we get our first sound example. Let's try that out. So now I'm gonna be moving from typing things into the interpreter here to typing them in my sapf file here and then evaluating them with option return. So just to show you how that works, I could say here 3 times 4 and then hit option return, and then, you know, it all goes in here and then we see the result at the end. And this is nice for working on longer pieces of code. So let's have a look at this. What does this mean? So clearly we have a number here, another number, then sign ask, then yet another number, 0.3, multiplication, and finally play. So to understand how this works, we need to take a look at what exactly sign ask does. So I'll type sign ask help, and I don't know what the @zz means here, but we can see that it takes the arguments frequency and phase and then outputs an output, whatever that is. So this is going to be the frequency, 800 Hertz. This is going to be the phase, 0. This is going to give us something. Let's actually see what ends up on the stack when we do this. Oh, that's interesting. So we get some sort of sequence on the stack. And here is, I guess, where we see our first difference from Super Collider. So it looks like the output of Eugens in this language is like directly a sequence of numbers or samples, and I'm assuming this is like an infinite sequence. And okay, then afterwards we had here a multiplication by 0.3, so that's just to scale the amplitude of the sign ask. So we can run that, and now we see everything has been scaled. And now we can try playing it. And indeed, that works. So that's pretty interesting. Let's go back to the README for a bit. Because right here comes a section on types, and this is going to be super important. There's a nice quote here by Alan Perlis, but the language has a bare minimum of data types. So one of them is real, which is 64-bit double position floats. So we don't actually have integers or 32-bit floats. A string, which is, well, a string, familiar from pretty much any programming language. A list, ordered lists of values that function as both arrays and lazy, potentially infinitely long sequences. So I think what we saw here was an infinite list. Then we have something called form, an object that maps symbolic names to values. A form is a dictionary with inheritance. Right, so like a key value map. Function, we have first-class functions. That's very good. Means we have a lot of abstraction power. Functions are values that, when applied, take values from the stack and evaluate an expression. And finally, we have ref, a mutable container for a value. This is the only mutable data type. So we can see here some inspiration coming from SuperCollider, I guess. Because SuperCollider has refs, it has functions, it has events or identity dictionaries or environments or dictionaries, which I guess here are just merged into one type form, and lists and strings and numbers, of course. So, syntax. Expressions are sequences of words or other syntactic elements written in postfix form. All words are executed in left to right order as they are encountered. When a word is executed, it looks up the value bound to that word. If the value is a function, then the function is applied, and any arguments of the function are taken from the stack. If the value is not a function, then the value itself is pushed onto the stack. So we have a fairly simple semantics here, I think. With, you know, words being either functions or not functions, and those have slightly different behavior, but that's basically it. And then here is explained this arrow notation, which just means that this evaluates to this. Comments, which we already saw. Numbers can be written in a few different ways. We got scientific notation, we got suffixes. This is also somewhat familiar from SuperCollider. We have these kind of scaling units. We have fractions, although I guess those become the real data type, so a float 64 instead of, you know, actual rational numbers. And I guess fractions can be irrational here as well, pi divided by 4. And that all looks very convenient. Strings, double quoted. We can escape for new line and for tab, and apparently we need 2 backslashes to do that. Words are sequences of characters delimited by spaces, square brackets, curly brackets, parentheses, or one of the quote characters described below, except for the equal sign, which can occur in a word. Okay, we saw this already. Quotes. There are certain symbols that, when immediately preceding a word, change the normal evaluation behavior. Normally, when a word occurs in an expression, the value bound to the word symbol is looked up and applied. For example, when a word appears by itself like this, and then there's the sign function, the interpreter looks up the value bound to the sign symbol, which is a function, and applies it. if a word is preceded by backquote, the interpreter looks up the value bound to the symbol without applying it. So when we prefix the sign with this backtick, then it pushes the actual function object that represents the sign function to the stack. And that's how we get, you know, this help feature. So help takes an actual function, but it needs to be quoted like this with the backtick. If a word is preceded by a single quote, the interpreter pushes the symbol itself onto the stack. Okay, and then there's even more. If a word is preceded by comma, the interpreter pops the object on top of the stack, looks up the value bound to the symbol in the object, and pushes that value onto the stack. I think there's some kind of like Lisp macro-like thing going on here. I don't fully understand this just from reading this. But maybe that's not super important right now. I wish there were some examples of what you can actually do with these two things. Maybe there's gonna be examples later. If a word is preceded by the equals sign, the interpreter binds a value to a symbol in the current scope. The current scope extends to the next closing square bracket. No mutable local variables. Symbols once bound may not be changed except at the outermost scope, the workspace. It is not possible to bind values to symbols outside the current scope. So this is basically how we can define variables. So let's say I were to write something like 5 and then equals foo. And this is gonna seem backwards if you're used to normal programming languages. But basically it's just saying that the variable foo is equal to 5. And that should allow me now to do, for example, multiplication of foo by itself. So this should give us 25. Yeah. And so basically now just typing foo pushes the number 5 onto the stack, because that's how we define the content of foo. Okay. There's some kind of multiple assignment syntax happening here. List unpacking basically also works for signals. Hold on, so now we're encountering the word signals, but what exactly is a signal? Did we miss that before? No. Okay. So it's a bit ahead. Okay, let's look at the functions bit first. So functions are a backslash followed by a list of argument names followed by a function body within square brackets. So this is kind of like reminiscent of Haskell's lambda syntax. So we have lambda a and b, the arguments are called a and b, and then this is like the function body. Let's see if we can already do something interesting with this. So maybe I'll just keep this up here. What's an interesting function? Okay, I don't know if there's a built-in function called lin, I guess not. It might be there by another name. But basically a function that I use all the time is the one that maps a number from one range to the other linearly. And in SuperCollider that's called lin. So just as an exercise, let's try writing that function. Whoops. So the lin function takes the input range, the output range, and then the number to map between those ranges. So I'm gonna denote the input range as L0 and R0, so left and right, and then the output range as L1, R1, and then the number to be mapped as X. And then we need our function body. So what do we need to do in order to implement this function? Well, first we need to subtract L0 from X. And in postfix notation, that's gonna look like X L0 minus. Then we have a number that we want to multiply by, that we want to divide by the difference between R0 and L0, basically the size of the input range. So I subtract these, and so as a result of this, we now have two numbers on the stack. One is X minus L0 and the other one is R0 minus L0. And we want to divide the first one by the second one, so then we just type a slash here. And this is where the unreadability of postfix starts to become a thing. Because in order to read this, you have to know that minus takes two arguments, and okay, that makes sense for minus. But in order to read a piece of code, you have to know basically the arity, or the number of arguments for each function that appears in that code, and it might be a different number than 2 or 1. And yeah, that's where reading this kind of code gets kind of challenging, but let's not worry too much about that right now. So as a result of this, we have now one number on the stack. Actually, let me write this out in like normal math notation so you can have an idea of what I'm doing. So we start with X minus L0, we divide by R0 minus L0. We want to multiply with R1 minus L1, and finally we add L1, and that's how you map from one range to another. So basically, so far we've implemented this. Okay, next we have now one number on the stack, and then we want to multiply that by this. So we push R1 minus L1 on the stack. Now we have two numbers on the stack which we want to multiply, so that's just an asterisk. And finally, to the result, we want to add L1 like so. Okay, that's a function definition. As it is, this is just an anonymous function, but we can give it a name with the equals operator. So I'll call it lin. And now we can try it out. So let's say we have a number in the range, I don't know, 0 to 1. So our input range is 0, 1. We want to map that to, let's say, a range from -10 to 10. And our example number is going to be 0.5. So now if I type linlin, it'll consume all of these items from the stack because it takes these 5 arguments and then push the result of this onto the stack. And we get 0, which is to be expected because 0.5 is exactly in the middle between these two numbers, and then 0 is exactly in the middle between -10 and 10. Let's try another number, for example 0. So we would now expect this to become -10. Yeah. Oh yeah, we still have the old result on the stack there. And if we do 10 here, then, or sorry, if we do 1 here, then we should get 10. So that's an example of how to write a function. A very useful function in music programming and all sorts of creative coding, actually. Okay, so we have an idea of how functions work. And yeah, here it also talks about assigning functions to a word to give them a name. A help string may follow the function arguments. Okay, so we could add some documentation. Let's do that. One thing I haven't really set up for this Emacs mode is indentation, and in fact I'm not really sure how to do indentation correctly for this kind of language. So it's kind of manual for now. So I'm gonna write a bit of documentation for this. The result of mapping x from the range L0, R0 to L1, R1. Okay, and now I think if I write backtick linlin help, then we don't get help for that. Maybe that's not implemented for like custom functions. I don't know. No, wait, sorry. I put the help string in the wrong place because it needs to go before the function body. Okay, yeah, it does work. Cool. My bad. And here's an interesting thing. Unlike other concatenative languages, the body of a function is executed on an empty stack. Values from the calling stack are not accessible except via the named arguments. That's an interesting difference, kind of like hygiene type of thing, that you can't accidentally access, you know, values from the stack that you didn't mean to, or something like that. Anyway, next up is lists. Lists are created by writing expressions within square brackets. So this is very simple syntax. We can also do math within these list expressions, use variables. Oh wait, this is not a variable, I think this is a function. Hold on, so if I have one AA, okay, I think AA is like a duplication function. And then there's BA here. Hold on, so let's say we have 1 and 2 on the stack, and then BA. Okay, so BA just swaps the last 2 elements. Okay, so there's an interesting naming convention here, from what I can tell, which is that we have functions named like AA, AB, and so on, and that's basically just saying that if our stack looks like A, then AA on that will basically produce AA, which is in the name, right? And if we have AB, then the function BA will produce BA. That's kind of cool. I don't know if this is taken from some other stack-based language. I don't think I've seen this before. Just a second. Need to update my playlist here. There we go. Okay, let's get rid of that stuff. So here comes that one interesting thing I was wondering about earlier. So there are 2 types of lists: value lists, aka streams, and numeric lists, aka signals. Signals are defined using an initial hash character as follows. Okay, so when we have a hash, that's a signal. But then I wonder, is it possible for both of these types of lists to be infinite as well? It would kind of make sense. Okay, forms, also known as dictionary map or record, a form is a set of bindings from keys to values. Forms may inherit from other forms. So it's just curly braces with colon in front of the keys. Okay, and then this is the inheritance. So if X is already a form, then putting it inside another form definition is gonna like expand the elements of that into the new one. And then it adds this C3, so I guess we get A1, B2, C3 in the variable Y. We can also put the keys in this weird order. So I guess like the order between the keys and values doesn't matter. All that matters is that the first key gets mapped to the first value, the second key gets mapped to the second value, and so on. This can be useful when returning multiple values from functions and binding them to multiple keys. Okay. Multiple inheritance. Right. Auto mapping. So this is kind of like multi-channel expansion stuff in Super Collider. Okay, I have a guess already as to how this works. So for example, if I clear the stack, let's say I have 1, then I have a list of 2, 3, then I say plus, then I imagine we would end up with 1 plus 2 and 1 plus 3 in a list. Yeah, that's exactly what we get. That seems like it's gonna be handy. Oh yeah, and we have this range operator, so we can go 0, 5, 2, and that just gives us a list with all the integers from 0 to 5. And the auto mapping works here too, and produces interesting results. Alright, so here it goes like 0 to 4, so we get that as the first element, and then 2 to 4, so we get that as the second element. Okay, that makes sense. But if lists are passed in for multiple arguments that are subject to auto mapping, then they will be auto mapped with successive values from each of the arguments. So we don't get like a Cartesian product where it would go 0 to 2, 0 to 9, 7 to 2, 7 to 9, but rather it goes 0 to 2 and then 7 to 9. Okay, that's good to know. And when multiple arguments are automapped, the result will be of the same length as the shortest list. Right. So here, basically, the 3 here doesn't do anything. Maybe performed over infinite lists. Okay, interesting. So we have the ORD function, which is going to give us an infinite list starting from 1. So I guess we could get with that okay, I want to do some kind of exercise with this just to kind of grasp how this works. So let's say I want to make an infinite list based on some mathematical function. So for example, let's do powers of 2. Okay. And I want to start from the 0th power of 2. So I think in order to get a infinite list starting from 0, I could do ORD 1 minus. So basically that subtracts 1 from each of the elements of ORD. Okay, and then how do I map 2 to the power? Like I can do 2 and power, but this gives me not powers of 2, but squares of the numbers. So yeah, we get 0 squared, 1 squared, 2 squared, 3 squared. So that's a bit different. I think I might have to use a function here. So let's say we have a function that takes x, then we want to raise 2 to the power of x. Okay, Let me add a clear here so we start with a fresh stack every time. Okay, so now we have the list on the stack, then followed by a function. So we need to apply the function somehow. A function may be applied using the exclamation mark operator. So we just put exclamation mark here. And that gives us our powers of 2. So 1, 2, 4, 8, 16, 32, etc. Okay. That's very good to know. I wonder what ord stands for. Is it like ordinal numbers or what? Well, it can't be the full set of ordinals if we get all set theoretical about it, but... well, infinite series of integers ascending from 1. Oh, hello, Ted the Trumpet. Nice work on the powers of 2 there. Thank you. Yeah, doing some basic exercises at this point still. Okay, where were we in the README? Here, I think. The each operator. Sometimes an operator needs to be applied at a deeper level than the top level. The @ sign, known as the each operator, tags the top value on the stack so that the next function that consumes it will operate over each of its values instead of the list as a whole. Okay, so what exactly does that mean? So let's say we have 0, 1, and 2 here. I think I'm gonna name this function. Can I call it 2pow? Yeah. Let's clear. So now if I apply 2pow to this, then that works as expected. If I apply @ then if I understand this correctly, this should have the same result. Okay, yeah. So what can we do to make it different? Well, I guess we can look at the example here. Say we have the following nested list. If we reverse it, we get the outer list reversed. What if we want to reverse each of the inner lists? We use the each operator. Okay. I see. Is there some other interesting example we could do with this? Can we write a Cartesian product, I wonder? So, for those who may not remember or know what Cartesian product is it is that if we have, let's say, lists like this, then we should end up with a list that combines... Okay, let's make this shorter just for ease of typing. So we should get a result where it combines each element from this list with an element from this list So we would get 0, 4, 0, 5, 1, 4, 1, 5. Or maybe it's easier for now if we think about this in terms of, for example, addition. So we would get a list with 0, 4 plus, 0, 5 plus, 1, 4 plus, 1, 5 plus, which is the same as 4, 5, 5, 6. Because now if we do just do plus on these lists, then we get 4 and 6 because it's like pairing this one with this one and then this one with this one. If I do each here, does that fix it? Not quite, I don't think. I need to think about this. Or if you have any suggestions in the chat, feel free to tell me. Also, I need to put more music on. Let's go with one of my older albums, Reveries. Okay, let's try to write a function for this. So we will take as argument a list of x's, a list of y's, and then we need to do something to apply the addition in a pair, or like in a Cartesian combinatorial fashion, whatever you want to call it. So if I now just do this, then this is the same as what I wrote before. Oh, and I need the apply here as well. Oh, I don't need the apply here, I think. I need the apply here. Okay, let's see. So that gives me those two elements. If I do this, then it gives me... I mean, this is basically doing the right thing already, but it's just... the result is nested and not flat like I would want it. Okay, is there something like a... Yeah, I guess that's one way to do it. One flatten. Okay, so that way we get our Cartesian sum, I guess. Now if I add another element here, then we should get a list with 6 elements, with the last ones being 0 plus 9 and 1 plus 9, which is 9 and 10. just like we see here. All right. Let's leave that and move on. Yeah, kind of related things happening here in the README. Oh, hold on, what's this? Ordered each operators. So that sounds to me like there is another way we can write this, which is gonna be maybe something like at 1, at 2, and then plus. But it still doesn't do the flattening. Okay, I don't want to spend too much time on this little exercise, so let's keep moving forward so we can maybe get to sounds. Cartesian success too, yeah, I suppose. Infinite list of infinite lists of finite lists. Fun. But okay, I'm gonna skip a bunch of this stuff now. Okay, then we have actual multi-channel expansion, a kind of automapping for operators that process signals and not streams. For example, unit generators. These operators automap over streams, but not signals. So the SAW oscillator expands over the list 300 to 301 to produce stereo channels that beat with each other at 1 Hz. Okay, let's try that. It's a bit loud and also higher than I wanted. So if you have stereo sound, you'll hear kind of like a stereo effect going on there. Thinking about this bit here, these operators automap over streams but not signals. Okay, so I think what that means is that if I had here a signal, I don't know how to write it, but let's say I had here a sine wave going from 200 Hz to 300 Hz, then that would be a signal, and then the SAW does not get auto-mapped over that, because that would produce like an infinite number of sawtooth oscillators, but instead, when the input is a signal, it just uses that as like the time-varying frequency for the SAW. Reducing and scanning math operators. For all 2-argument math operators, adding a forward slash after the operator turns it into a list reducing operator, and adding a backward slash turns it into a list scanning operator. Oh, that's kind of neat. So we don't need a separate sum function, for example. We can just do plus slash. So that just adds everything in the list, and we get that. Likewise for product. And then with the backslash, it's like scan R and scan L in Haskell. I guess this would be scan L. So if you're wondering how this works, it's like first we take 1, then we take 1, 2, and add those. No, wait, am I wrong? Oh, sorry, I was doing multiplication, not addition. So yeah. Then we do 1, 2, 6, multiply those, and finally we do 1, 2. No, what am I talking about? 1, 2, 3. 1, 2, 3, 4, and so basically each element is like it takes one more element from the original list and then does the multiplication or whatever operator is here on like that prefix of the list, I guess. Alright. Adding a caret after the operator makes it work in a pairwise fashion. Hold on. It outputs the first value, then outputs the operator applied to successive pairs. So here we get 1, the first element, then I guess we get 1 plus 2, then 2 plus 3, 3 plus 4, okay, and so on. I see. I wonder if this can work for like user-defined functions as well. Because I think like this is not a function of its own, it's the plus function suffixed with the caret. What would be an example of a function to try? Do we have, I don't know, LCM? Or GCD actually. So the greatest common divisor, it's gonna be 6 for these. And 2, 4, 6, and 8. So can I do a list of numbers and then say GCD slash? I can. Interesting. So then I assume it would work for basically any function that takes 2 arguments. Let's say we have what's a good function? I could do something like an average. Is there already one? Maybe not. Okay, let's write an average or mean. So for that we just add x and y, then divide by 2, and we'll call that mean. does this mean I can now do this? Oh, apparently not. So there is some kind of magic that happens here to make functions compatible with this. What is it? Reduction or scanning. Gotta go now, thanks, interesting stuff, way above my head. Hey, thanks for joining. Yeah, I guess this can be very confusing if you haven't used a stack-based language before, and also there's some like Haskell idioms going on here, so it's a lot. Okay, I'll add here a to-do for myself. What makes functions compatible with reduce or scan? Just as something to figure out later. And interestingly, with that we are at the end of the README. So yeah, the documentation is maybe not fully fleshed out yet. However, there is a file with examples. Okay, so these get a little bit more complicated immediately. Let me reorganize my windows. So there's an interesting thing here, which is this example as a form, a sound as a form, a longer way to write the same example but not parameterizable. So what's happening here? We are first defining this form or dictionary or whatever you want to call it with keys such as rate 1 is 0.4, rate 2 is 2 different values actually, depth 1, blah blah blah, various parameters. And then we have a entry here that is a function. And I think, okay, so we have like a field access syntax, so most likely the O here is gonna be like this entire form. I guess O might stand for object or something. So we can, if we're thinking in like object-oriented programming terms, then O here is like the this variable or self from many OOP languages. So the out is kind of like a method actually, and it accesses all these parameters and it builds up an expression from them, which I guess results in some kind of signal graph. Here we see one issue that currently happens. So when we have multiple lines of code and I run it in this Emacs mode, then although my mode is sending everything at once, I think there's like some line buffering. Maybe the sapf executable forces line buffering so that after every line it like processes that and it outputs this, prompt here, and it's kind of slow. So evaluating a multi-line block like this takes a few seconds even, and that's not great. But I think that's something that needs to be fixed on the sapf side rather than my Emacs thing. Although I was thinking that there would be one way to maybe work around it, which would be to send everything as one line. But then I would have to detect comments in the code and strip those, because otherwise if I merge these into one line, then, you know, the comments are gonna mess it up. So I haven't implemented that. Okay, but so this defines a form and calls it analog bubbles. And then here we see how to actually play that. So we access the out field and okay, let's take a step back, look at what is play actually. So play just takes channels. So I'm guessing channels here is a signal. So a single collection basically of samples. Okay, interesting. So by accessing analog_bubbles.out, it seems we already get a signal. So I think when we do this, it's already like magically passing the O argument here and executing this function body. That's the only way this makes sense to me, because like I would expect this otherwise to return a function. But this is not a function, this is a list of signals, because it's a stereo thing. Yeah, that's kind of interesting. What about other keys here? For example, depth 1. Yeah, so that works normally. I wonder if there's a way to get like the function. Okay, now I wonder if dot is some kind of special operator. Guess not. Yeah, I'm not entirely sure how this works. What if I just say analog bubbles dot? Okay, yeah, so it is actually a syntactic element that requires us to have like both sides of the dot. Okay, yeah, I don't know if there's a way to get like this actual function without executing it, but maybe it doesn't matter for now. So let's just do play here. So that's a nice example of some sounds. Let's try to figure out what's actually happening here. So we start with center, and so this is a number of semitones. We create a low frequency saw with rate 1 and phase, or rate from this rate 1 field and a phase of 0. We multiply that by depth 1 we add that to center. So after this we should have just one value of on the stack. We can actually check that. We can put a print stack in the middle here. So yeah, we just have one signal at that point. Then we make a second low frequency saw multiplied by depth 2. And then we add that to our first one. And now the way I'm reading this, okay, let's look at what NNHC is. I have an inkling. Yeah, convert MIDI note numbers to hertz. 60 is middle C. That makes sense. So basically what we have as a result of this is some kind of oscillator that produces numbers that represent MIDI note numbers. And then with this we convert those to hertz. So at this point we have an oscillator that produces frequencies in hertz. Then we give phase 0 and that hertz time varying to sine osc. So here we have just a sine oscillator with varying frequency. Then we take the dB number here, convert that from decibels to amplitude, multiply by that. Then I guess we use comb n to apply a delay. And comb n takes input signal, which would be all of this, delay time, maximum delay time, decay time. Okay. So I mean, it's not super hard to figure out how these things work, but as I said before, you kind of do have to know the arity of these functions, although the way this is split up into lines helps us a little bit here. Because the way this is structured now is that after each line we have one thing on the stack, and then that gets used by the next line as an input. So yeah, that's not too bad. This is something I'll have to keep in mind while writing my own functions as well. Okay, let's try to actually make some of our own noises. What would be a good thing to try? Well, there's always one of my favorite things, which is a super saw. So let's try writing that. I'm also gonna use this form style. So our out will be again a function that takes O, which is the whole object, then it does something. Okay, how do we parameterize our super saw? So a super saw is some number of sawtooth oscillators which are detuned and often also spread in the stereo field. So I guess one of our parameters is going to be the number. Let's start off with 2. Another parameter could be the detuning. So let's say this is going to be in semitones. And basically this is going to express how many semitones from the center frequency the outermost, or like the last sawtooth oscillator is going to be. Let's say something like 0.2 semitones. And then I mentioned the center frequency. We're going to need to specify that as well. Let's go with 220 Hertz. Okay, so how do we get started? Let's actually use 3 oscillators, just so we have one in the center that actually plays the center frequency. So to do this, we're gonna have to create 3 things. And we saw earlier that we can use the function 2 to make a list from like a numeric range. So let's say we want to make a list from 0 to num minus 1, so in this case 0 to 2. How do we do that? Well, we push a 0, we push o.num, we subtract 1 from o.num, so now we have basically 0 and 2 on the stack. Then we do 2. So as a result of this, we have our list of, I guess, oscillator indices. And I think we're gonna need this multiple times, so I'm gonna actually assign this to a variable called indices. And I guess we can't play this yet, but we can just run this to check what happens. Huh. We get just 0 for some reason. Wait, do I need to push this? Okay, yeah, that makes sense. So that's our list of indices that we're working with. Then we need to turn that into a list of, let's say, a list of semitone values to detune by. So basically I want to convert this list of 0, 1, 2 to a range between, well, I want to convert from a range of 0 to 2 to a range from -1 to 1. And luckily we earlier wrote this linlin function here. I'm gonna just attach it here so we have everything in one place. So we have a function to do that. So basically, again, we're gonna need to I don't like the repetition here. Let's do o.num -1 and call that I max, so that's the max index and then we can use that in multiple places. So this is our input range, 0 to imax, and then our output range will be -1 to 1. And then our thing to map will be indices, and now I expect that even though indices is a list, the auto mapping will take care of applying our lin to each of the elements. Okay, so what do we expect now? I would expect this to result a list that goes -1, 0, 1. Let's try it out. Yeah, that's exactly what we got. Good. Now that I think about this, actually this is the list that we're gonna need multiple times. So I'm not gonna bother naming indices. Or maybe I will actually. It's fine. It makes this more readable. I'm gonna call this result positions. Okay. And then we need to turn our positions into a list of detune amounts. Oh, hello, Raphael. What on God Green's Earth are you coding? This is James McCartney's new audio programming language, sapf, or Sound as Pure Form. It's a weird stack-based language, and also I realized that my TikTok chat overlay stopped working. Let me just restart that. Okay, that's better. Yeah, so we have positions, and we need to turn that into a list of detune amounts. Well, that's easy. We just take positions and multiply by detune. And now, in fact, with this, we should have a list that goes -0.2, 0, and then 0.2. Oh no, I made a mistake somewhere. Oh yeah, this needs to be o.detune, because it's a member of the object, or the form. Yep, here we get what I expected. And then this is fairly easy to now turn into a sawtooth wave. Basically, we just give a 0 phase and we say saw, right? And then I do want to multiply that by, or I guess divide by the number of oscillators, so we get a nicely normalized value. Let's put that on its own line, and then I can scale that down a little bit more just so we don't make it too loud. So now this should give us, let's see what it gives it. I think it gives us like 3 signals, so basically a 3-channel sound. But of course we only have stereo, so I want to mix these together. For now, let's just mix to mono and see how that works. That's easy. We just do the plus reduce from earlier, so this will sum all of these. And we should end up with just one signal. Okay, now I should be able to play this. Let's try. I don't hear anything. Oh, I think I know why. It's because this here is now just the D tunes, so this will give us some very low frequencies, so we're not going to be able to hear those. What I actually want to do with this is process them a bit further. Hold on, so what's gonna happen? We need to turn these semitone based detunes into multipliers, or like factors. Ratios is the word I'm looking for. So similar to the NN Hertz function that is built in, I wonder if there is like a NN ratio. Maybe not. That's something we do have in Super Collider. Okay, well, that's no problem. We'll just define our own version. And how can we do that? Well, we can use NN Hertz. So let's say we have N, we compute what that is in Hertz, then we compute what the MIDI note 0 is in Hertz, and then we just divide those by each other, and we call this NN ratio. Let's see if that works. So now if I have, let's say, 12 semitones, that should give us a ratio of 2. Yep, and minus 12 should give 0.5. Yes. So I'm gonna plop that up there as well. Okay. So then we apply NN ratio to what we have here, which is the detune amounts. So now we have detune ratios basically. And each of those, I guess we just want to multiply by our base frequency, which is O.freq, and multiply. And then we can give that as the frequency of our sawtooth oscillator, and now all of this should work. Yeah. We have our first super saw. I can increase the detune here a bit. And it gets more detuned, as you might expect. Okay, but this is now just mono. It's not doing the stereo spread that I like to have. So how could we do that? Instead of the plus, we'll need to do something different. Right, this is where we'll need the positions again. First, I need to see if we have like a pan function. Maybe it's pan 2. Yeah. So it takes input, position. well, the input is everything we have here. And as the position, we can just pass our positions array. I named this one with some foresight. And then we give those things to pan 2. And now we should get a nice spread out supersaw. Or not. Okay, I wonder what went wrong there. Let's try to just look at what ends up in the stack. Oh, hold on. Okay, so we have a list of lists of signals. Oh, okay. So this gives us basically now 3 stereo signals in a list, but we want to add those together to get our final output. Yeah, now this looks like a stereo signal, so if we try to play that... Yeah. Now, of course, you'll need to have stereo to really get the effect there, but... Okay, and then we can try some other values for our parameters. Let's decrease the pitch and increase the number of oscillators. Maybe we can go even lower. What about maybe smaller detune values? Pretty cool. What about something larger? We could get a bunch of octaves if I do something like this. Okay, it doesn't sound that great. But yeah, the octaves are there. Alright, we have our supersaws. What about, let's say instead of hard coding the saw here, I want to parameterize that as well. Would that be something like... Oh, hello, Kuno. Sounds cool. Thank you. So let's say we have a function here called ask, and that's gonna return... I'm not sure how this is gonna work. Because I wanted to take one argument, and that's gonna be the frequency. I'll call that f here. But... Okay, let's start off just by using the same saw. So I think maybe now by saying o.ask, this should do the thing. No. Wrong type for saw, frequency, expected real or signal, got form. So, okay, maybe these go the other way around then. Okay, yeah, that works. Are you using a framework for this? Well, I don't know if it can be called a framework. It is sapf, which is James McCartney's new audio programming language. Sound as pure form. It was open sourced just recently, yesterday in fact, and currently only available for Mac OS, but maybe that will change now that it's open source. Right, so now that I have the saw or the oscillator parameterized, I can try other ones. I assume there's one called pulse, frequency, phase, duty. Okay. Let's go with just a static duty cycle for now. Pulse. Nice. But now I'm thinking, can we add some movement to the individual oscillators? Is there an LF noise, for example? No. Ah, yeah, it's named like in Super Collider, so we have LF noise 0 and 1, but not 2. Okay, that's fine. So LF noise 0 is like stepped noise. It changes, you know, discretely from value to value, but then LF noise 1 is like a smoothed version of it. So here, instead of putting a duty cycle that's static, I could make it vary with LF noise. But to do that, I need to map the output of this to a given range, and I could do that using the lin function, but I assume there is something built in for this special case. Maybe by-lin, by-range, because I feel like I saw something in the examples. Let's see. Yeah, here is something called by-lin. Ah, okay, it's defined here. Oh, I think we should actually be using this prelude file, because there's a lot of useful things in here, from what I can see. Okay, how do I actually do that? I need to go into my Emacs file and pass that as the argument. What was the argument called again? P for prelude file, makes sense. Where is my prelude? There. Okay, I think with that, maybe that should just work. I need to restart. Could not open, so maybe I need to get rid of the tilde there and actually have the absolute path. Like so. Yeah, that works. So now I think we have violin, and do we actually get lin as well? We do. So I can get rid of my own definition here. I also want to check whether there is something for this ratio thing. I guess not, so we'll keep the NN ratio function here. Then... Okay, so what was I doing? I wanted to use LF noise, and then I want to map that to some range. Okay, so in place of the 0.5 here, we're gonna put LF noise 1, except this needs to take one argument, which is going to be the frequency that the LF noise like oscillates at. Let's say that 5 hertz. And then we need to... Alright, now the ratio, or the range comes after the argument here. And that also applies to lin, so I think I need to move these to here. And then this is gonna be violin, and then here is gonna be my actual range. So I don't know, let's go from 0.2 to 0.5. That's a nice range of pulse width. Maybe 0.1 actually. Let's try that out. Stack underflow. So I messed up something here. So this definitely produces just that one signal, which is what I expect. I think the error has to be somewhere else. Oh yeah, lin goes here. Try that out. Let's try with just one oscillator at first. Oh, it crashed. That's no good. Okay, I'm gonna save that as an example of something that seg faults. I wonder if the issue there is that we're going 002. No. Yeah, not sure what exactly goes wrong there. Let's try. Okay, so we get this far. Let's just sprinkle some print stacks in here. Okay, we're getting not a number somewhere. I think that would have to be here. Oh, right, okay. It's because I'm putting Imax here, which is 0 in this case, and then 0, and then we end up doing division by 0 somewhere in the lin function. Okay, that's interesting. How do we avoid that? Do we have something like an if function? If A is true, then apply B, else apply C. Right, so we need to check here for the case that Imax is 0, I think. So if, okay, let's see. Okay, so we have double equal sign as comparison or equality. So if Imax is 0, then we are gonna apply B, else apply C. So I guess we need to write these things as functions. Oh, hello, Igor NPC. Nice first intro to sapf. Do you think that sapf can be ported to Linux? James wrote about changing AU audio to RT audio. Do you think this is complicated? It's hard to say because I haven't looked at the internals yet. I'm just, playing around with the interpreter here. I mean, from what I can tell, this is C++, although there is some Objective-C in here, I guess. Yeah. But I mean, Objective-C can run on Linux. But yeah, without really diving into the source code, it's hard to say how much this is making use of Mac OS thingies. And yeah, I also saw in the issues that replace audio unit playback with RT audio. And RT audio is this cross-platform audio API. So seems like there's kind of an intention to make it cross-platform, but yeah, I don't really know how much work it would take without looking more closely at the source code, which I was thinking about doing that on this stream as well, but I don't think I have the energy for that after first a long work day and then just playing around with this, but maybe another time, unless James or someone else gets there first. But yeah, of course, we're all hoping that this could be cross-platform eventually. But I mean, this is how Super Collider started out too, right? Version 1 and 2 of Super Collider was only for Mac OS. Then when Super Collider 3 got open sourced, I think I'm not sure if James did the initial porting there to like other platforms or if other community members stepped in to do that. But yeah, I guess we might have like a similar trajectory here, depending on how much interest there is in this new language. Right. So I was gonna do an if statement or expression or function or whatever you want to call it. So if Imax is 0, then we don't actually want to do anything to the stack. And I think indices should in fact go here. I'm not sure how to indent this logically. But anyway, in this case, we don't want to apply the lin thing. So we'll just take a value from the stack and push the same value. But in the else case, we wanna do this basically. And add an X there. So, yeah, again, what I said about readability of stack-based languages, it gets, in my opinion, really strange with these reverse order if expressions. So, the way we need to read this if is, if this here is true, then we do this, otherwise we do this. So it's kind of, you know, jumping back and forth. I'm not sure if this argument order is the most logical one. I feel like maybe if the condition was like the last thing here, maybe that would make sense, or not, I don't know. Okay, anyway. So ideally that should take care of our segmentation fault. Yeah, looks like it did. Nice. Maybe I want to take down the frequency here a bit, maybe 1.7 Hertz. of the LF noise. And also maybe the frequency could be different for each oscillator. I wonder if there's like a, yeah, rand. So let's put a random number here between, I don't know, 1.5 and 4. So that way we get a bit of movement per oscillator, but I don't know. I feel like there could be more. So for example, we could, within the oscillator, also detune the frequency randomly a little bit. Maybe I'll split this into multiple lines somehow. So instead of F, I want to have something like let's parameterize this as well. I'll call it detune 2, and it can be a smaller number. So we'll have an LF noise again. We'll have that go from negative detune to, do we actually have a negation function? Yeah, that's, I think, better. Violin, and we need to give a frequency again. Let's do another random one, and now from 3 to 8. Then this one we need to convert to a ratio again. And then we multiply that by F. Yeah, that's starting to sound like fuller. I still want to add one bit of per oscillator movement. I'm assuming we have filters. Yeah, LPF, maybe resonant LPF. Yep. So we're gonna filter the pulse oscillators. So for that we're gonna need, I guess, another LF noise will do. Wait, no, what do I want to be my frequency range? Let's say we want to go from 200 to 8000 hertz. So that's gonna be our frequency for the LPF, or the RLPF. The inverse Q can be, I don't know, 0.7. Is there a bi-exp? Yep. So we're gonna map something exponentially from a bipolar range to this range, and that something is gonna be another LF noise 1, and the frequency of that is gonna be, let's make it another random one between, I don't know, 0.5 and 3 hertz. Oh, I misspelled RLPF. This code is getting too long to fit on the screen. Oh, hold on, that didn't work. Interesting. I mean, there is some output we can see, but it's not audible, so what did I do wrong? Oh, I forgot the rand here. Okay, I'm not noticing a bug here, which is that we're getting the same filter and presumably also the same random detuning and the pulse width modulation for each oscillator, and I think that is because I'm applying it just like this, but maybe if I do the each thing, then maybe that'll fix it. Also, I can get rid of all the print stacks here. Yeah, that's what I wanted. Let's turn that up a little and maybe increase the RQ here. I want to try this without the filters. By the way, one thing I did with the Emacs mode is that it supports, or like it's aware of the comment syntax, so I can do the keyboard shortcut to comment and uncomment lines and it just works, which is very handy. I think now the dtune 2 might even be a bit too much. Let's do like 2 semitones. I like it. I could try also some delay on this just for fun. So we take in delay, max delay. Decay time, let's say, I don't know, 4 seconds. Oh, but this is now only the delayed signal. Okay, so I can duplicate the input signal with AA. Then one of those becomes the delayed signal, and then I can just add them back together. Yeah, that works, but I think I'm gonna give these names. So this is gonna be asks. This is gonna be delay, and then at the end I wanna do just the sum of asks and the delay. Because there's something more I wanna do here. Hold on, get rid of that plus. What I want to do is also filter the delayed signal. Do we have our BPF? Ooh, no we don't. Our HPF is there. What about just BPF? Okay, I'll try our HPF. So we get our input, we get our frequency, we get our RQ, which I'm gonna put at 0.7, and the frequency is gonna be I'll have that vary from 100 to 2000 by exp, and we put another LF noise 1. And I guess the frequency can be something pretty slow. I think I forgot to apply the RHPF. I'm gonna put a bit more feedback on the comb N, let's say 7 seconds. And also I'm gonna turn the RQ way down or up depending on how you look at the effect. I'm thinking I actually want to filter before we go into the delay. I also feel like the delay could be maybe just a little bit louder. Okay, let's try more oscillators. Maybe the delay is not too loud in relation to the dry signal. Yeah, I'm liking it, but I'm wondering if we can get like really high Qs here. for some proper resonance. Yeah, that's more like it. Here I'm kind of feeling the need to start naming things because this is getting out of hand. Let's call this the pulse width, then we pass that to pulse. This can go here. This is gonna be the frequency. This is gonna be the filter filter frequency, let's just call it fill freak. And maybe it becomes a bit more readable this way. And we could have the Q also vary over time. I'm just thinking about adding a fundamental sine oscillator here. I think I saw some errors up there. So what's going wrong? LF noise is an undefined word. Okay, of course it is, because we need the 1 after it. See, now we've got some bass. I feel like there's like a limiter or maybe master clipper on this. Because it never goes into the red when it's just the output of this playing. I mean, when I speak into the mic then it goes into the red, but that's just... that's different. Okay, that's nice, but this is not really a super saw anymore. I guess I'll just call it a drone. And I wonder if we can do something like a fade in. Yeah, we have lines at the very least. So let's try 4 seconds going from zero to 1 line, and then that's not really gonna be perceptually uniform because it's like, you know, decibels are logarithmic, whereas this is linear. But let's try this out as a first attempt. Ah, but it stops afterward. Interesting. I wonder if there's a way we can get around that. Right, that's an exponential line. basically just searching for a way to do a nice envelope that doesn't stop the synth after the envelope is done. Because line seems to do that. Okay, so lines is basically, I think, the equivalent of env in Super Collider, in that we can specify like a multi-stage envelope. But that's not really what I want. I guess we could just build this using the sample rate. Okay, so I'm gonna make a function called fade. It's gonna take iteration. We're gonna start with ord. We're gonna subtract 1 from each element. We're gonna divide each element by the sample rate. Actually, we want to multiply the sample rate by the duration and then divide by the result of that. I think. And then we want to take the minimum of 1 and that. Wait, there's no min function? Oh, that's interesting. Okay, so I guess we'll have to define min as well. xy. If xy is... If x is less than y, then we return x, otherwise y, and then we wrap that in if. Let's try this first. Yep. So we're calling this min. And that lets us define our fade function. Let's say we wanted to do something like this multiplied by 0.3. Does this work? No. And that's because I forgot the phase. Indefinite operation. Oh, I think it's because now fade is returning a list and not a signal. I wonder if I can convert between them somehow. Don't think there's an integrator either. This turns out to be a little tricky. We have infinity, it seems like. So I wonder if I can do... what was it called? Lines? Yeah, maybe something like... 0, 1, 1. Then our durations are gonna be, let's say, 2 seconds and infinite. And what is rate, I wonder? I guess just 1. Let's try something like that. That actually worked. Okay, great. So then fade becomes a bit easier, I think. We just do 0, 1, 1. Duration inf 1 lines. Throw that in there. No, maybe this will work. Yeah, then the one final thing I want to do with that is bend the curve of that, because now it's linear. Let's do to the power of 4, because that's a common approximation of like a exponential volume control. So something like this. I feel like maybe the decay time on the comb end is a bit too long after all, so let's try 5 seconds. Yeah, I'm pretty happy with that. The next thing I would really be interested in looking into is how to make something like sequences or patterns. But to be honest, I'm getting a bit tired, so maybe I'll leave that for another time. So yeah, that's maybe gonna be it for tonight's stream. That is a first look at sapf, James McCartney's Sound as Pure Form programming language. Again, you can find it on GitHub. User lfnoise, repository sapf. Only Mac for now, hopefully other OSs in the future. I think I read in one of the examples that there is in fact MIDI control, but I don't know how exactly that works. Don't know if there's OSC, maybe not. That would of course be a great addition. Don't know if there's a way to do like patterns, but I would imagine there is. But anyway, another time. Also, I would like to add some kind of syntax highlighting to my Emacs mode here, but it's gonna be a bit of work because you have to either deal with Emacs syntax tables or write a tree-sitter grammar or something like that. And it sounds a bit tedious, to be honest. Maybe if someone else writes a tree-sitter grammar, then we can bring it into Emacs as well. But yeah, that's it. Thank you for joining me tonight in exploring this strange and interesting new language. As James says, it's not intended to be a replacement for Super Collider, and for me, I don't think it's gonna be anything like that, but it's always fun to experiment with new things, and I do see a certain elegance in this programming paradigm that is quite pleasing, even though the code ends up being hard to read. But I don't know, maybe that's something you get better at with some practice. But yeah. Like, follow, subscribe, push all the buttons. Buy my music on pulu.bandcamp.com. I have a new-ish album called Nested, out, made purely with code. Also, it was my birthday yesterday, so if you haven't bought it, you should buy it as a birthday present from me. Okay, thanks, have a good weekend, and I'll see you another time. Bye bye.